Welcome back, everybody. This is our 10th session in JEE Mains previous year questions for chapter Ray Optics and Optical Instruments of class 12th. Before this video, we have made 9 videos in this series and all of those are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing for NEET, then you can guide them through those videos also. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of our screen, or your screen, sorry, and donate us whatever amount you want. Any amount of help will be highly appreciated. With this, let's start the video. In the previous one, we covered around 70 or something, I think. Okay, we reached around 80, I think. So this was one of the last one. Okay, now we will start with the 78th. So here we have a beam of light consisting of red, green and blue colors incident at the right angle prism face AB. The refractive indices of the material of the above red, green and blue colors are given respectively. The person looking the surface AC prism will see. So we have to find whether which of the light here will able to cross. Now as we can say that incident light is perpendicular to the first face. So it will strike like this and this will angle will be 45 equal angles. So if we draw a normal here, so we will get 45 here. So we can say on this face, angle of incidence theta is 45 degree. Now we know normally for a critical angle, theta c is equal to sine inverse 1 by mu. Now we have three values of refractive indexes here. So what we will do, we will assume that for one of for any of these light, if theta c is equal to 45 degree or theta c less than 45 degree, then that light will be totally internally reflected. So we will solve it for 45. So from this 45 will be equal to sine inverse 1 by mu, and sine of 45 is equal to 1 by mu. From this mu comes out to be root 2 and that is 1.41. So it means if refractive index of any light is less than this one, and why less than? Because we know that critical angle is equal to sine inverse 1 by mu. If mu have the lower value, then this term will be as a whole will be greater and theta will be greater. So if mu is lower than 1.41, that light will be totally internally reflected. And here we have mu means refractive index of the red is lower than 1.41. So red light will be totally internally reflected, and we have here blue and the second one is green. Blue and green will pass and red cannot. So we will see green and blue colors. So option B is the right answer for this question. Let us move ahead. Now a glass prism of refractive index 1.5 is immersed in water of refractive index 4 by 3 as shown in the figure. A light beam incident normally on the face AB totally reflected to reach BC. So it incident on the AB face and it's get totally reflected to reach BC. So path of light will be like this. Light will go like this and it will then totally reflected to reach face BC. So as it is incident normally, so this angle will be 90, and if we draw the normal here, this angle will be 90 minus theta and this angle will be theta. Now, as mentioned here, that light is getting totally reflected. So this theta should be greater than equal to the theta c. So we will solve for the theta equal case. So theta is equal to theta c, and theta c will be equal to sine inverse 1 by mu. Okay, so if we write in this form, so we will get theta is greater than equal to sine inverse 1 by, here this is the refractive index of the prism, and we have a refractive index of the environment also. So refractive index of the prism divided by refractive index of the environment. So theta will be greater than equal to sine inverse. Refractive index of the environment or the water is 4 by 3, and of the prism is 1.5, that is 3 by 2, and 2 will be here. So theta will be greater than equal to sine inverse 8 by 9, or we can write that sine of theta will be greater than equal to 8 by 9. That is option C here. Now let us move ahead. So which of the following process play a part in the formation of rainbow? So in case of rainbow, suppose this is a water droplet. So what we have? We have a light incident, light entering like this. Then we have a refraction here. Then we have a total internal reflection here. Then we have a refraction here. So we have refraction, total internal reflection, and again a reflection. This is the case for primary rainbow. Even in the secondary rainbow, what we have two total internal reflections. So interference is not there, interference is not there, dispersion is there, because due to refraction dispersion is also there, and TIR is also there. So we can say 1, 2 and 3 can also be included. So that is option A, 1, 2, 3. So now coming to the next part. The refractive index of the glass is 1.520 for a red light and 1.525 for blue light, and D1 D2 the angle of minimum deviation for red and blue light respectively for the prism of glass. Then we have to find that how these angles are related to each other. Now we know for a thin prism, angle of minimum deviation is equal to mu minus 1 into A. So delta M is directly proportional to the refractive index. Now here we know that refractive index of the blue light, sorry, mu for the blue light is greater than mu for the red light. So using this proportionality, we can say delta M for the blue light will be greater than delta M for the red light. And for the blue light, it is D2. So D2 will be greater than D1. That is option A there. In the next one, a light ray is incident perpendicularly to a one face of a 90-degree prism and total internally reflected of the glass air interface. If the angle of reflection is 45 degree, we can conclude that refractive index n. So we have to find out refractive index n here. So we know that critical angle theta c is equal to sine inverse 1 by mu here. Now, as here a given angle is 45, that at 45 we are having total internal reflection. So theta c could be smaller or equal to 45 degree. We are not sure regarding that. So if we take sine of theta c, then it should be greater, less than or equal to sine of 45. Now sine of theta c from this is equal to 1 by mu. From this relation, sine of theta c is 1 by mu is greater than is less than equal to sine of 45, that is root 2, and from this mu will be greater than equal to root 2. So that is option B for us. So option B is the right one here. Now in the next one, A compound microscope consists of an objective lens of focal length 1 centimeter, eyepiece 5 centimeter with separation of 10 centimeter. The distance between object and objective lens at which the strain of the eye is minimum is n by 40, the value of n. Now, here for the no strain condition or the minimum strain condition, the image by the eyepiece will be at infinite. So here we have objective focal length as 1 centimeter, eyepiece focal length as 5 centimeter, and our distance between them or separation between them is 10 centimeter. So using the lens formula for the objective lens, and here one thing also, that suppose this is our objective lens and this is our eyepiece. Now we know that final image of the eyepiece is at infinite, so its object must be at its focus, and focal length of the eyepiece is 5, so this distance is 5 centimeter. Now their separation is 10 centimeter, so objective must produce an image at a distance of 10 minus 5, that is 5 centimeter. So we can say V of O is also 5 centimeter. So from this we can use lens formula that 1 by V of O minus 1 by U of O is equal to 1 by F of O. So that is 1 by 5 minus 1 by U of O is equal to 1 by 1. And when we solve this, we will get U of O is equal to minus 5 by 4. And that has to be represented as n by 40. So what we can do, we can multiply by 10, divide by 10. So this will be minus 50 by 40. And if you take magnitude only, so this will be 50 by 40. If we compare it, the n is 50 here. Now moving to the next one. In a compound microscope, the magnified virtual image is formed at a distance 25 centimeter from the eyepiece. So V of E is 25 centimeter here, and this is virtual, so it will be positive, negative. The focal length of the objective lens is 1 centimeter, F of O 1 centimeter. Magnification is 100, so magnification MO is 100, and the tube length of the microscope, or we can say L or D, that is 20 centimeter. Then the focal length of the eyepiece in centimeter will be. So first we will start with the objective and then we will move to the eyepiece. So for objective, let us assume that U is equal to minus of X. So we can write that 1 by V of O minus 1 by negative X is equal to 1 by 1. Now from this, value of VO is equal to X minus X1. Now magnification M1 will be equal to V by U, VO by UO. Suppose that is UO for the objective. So this will become X by X minus 1. And here we will have negative X. And what we will do, we will take the magnitude only. So this will be 1 by X minus 1. And this is M1. Now for eyepiece, as their separation is 20 centimeter, so U of E will be equal to 20 minus 1 by X minus 1. And we know V of E already minus 25. So M2 here, magnification due to eyepiece, will be equal to 25 divided by 20 minus 1 by X minus 1. Now as mentioned here, that total magnification is 100, and so M node will be equal to M1 into M2. Here this relation will hold. So if you multiply here, so this is M1, that is 1 by X minus 1 into 25 by 20 into minus 1 X minus 1 minus 1 by X minus 1 is equal to 100. This will cancel on 4. And if we take it further, so this will be 1 by x minus 1. Here we will have x minus 1, and here we will have 20x minus 20. So 20x minus 20 minus 1, I think, is equal to 4. So this will get cancelled out. And if we cross multiply it, we will get, this is 4 by 1 basically. So we will get 80x minus 84, 21 is equal to 1. So 80x is equal to 85 and x is equal to 85 by 80. So that will give us 1 and 7 and 17 by 16. This will give us value of x. Now we can come back here. We have the x, that is 17 by 16, and what we have to find? Focal length of the eyepiece we have to find out. So we can substitute here value of x, and that was, I forgot, 17 by 16. So u of e will be 20 minus 1 by 17 by 16 minus 1. This will give us 20 minus, this will be 17 minus 16 by 1, that will be 1 by 16. So 16, or this will give us 4 centimeter. So u of e we have, v of e we have, and this will be this we will take as negative because uh, object is in front of the eyepiece here. So we can write that 1 by negative of 25 minus 1 by negative of 4 is equal to 1 by fe. And if we go it further, so this LCM will be 100, this will be minus 4, this will be plus, and this will be 25 is equal to 1 by f of e, and this will be 21 by 100 is equal to 1 by fe. So f of e will be 100 by 21, and this will be approximately 5 centimeter. Approximately 5 centimeter. So answer to this question, that focal length of the eyepiece will be approximately 5 centimeter. Let us move ahead. Magnifying power of the telescope with tube length 60 centimeter is 5. The focal length of the eyepiece we have to find out. So here we have L, that is equal to sum of FO and FE as 60, and magnification, that is equal to FO by FE is equal to 5. So from this, FO is equal to 5 times of FE. So from this, 6 times of FE is equal to 60 and FE is equal to 10 centimeter. That is the eyepiece. So option D. For the next one, if we need magnification of 375 from the compound microscope of tube length 150 millimeter of objective focal length 5 millimeter, focal length of the eyepiece should be close to. So for a compound microscope, here length is 15 centimeter and f of O, that is 0.5 centimeter. Now magnification is given by f of O by f of E into 1 plus d by fe, where d is the distance of least distinct region, that is 25 centimeter basically. So magnification is 375 here. F of O is 0.5 divided by f of E into 1 plus 25 by 0.5. Oh, sorry, f of E we have to calculate. So f of E, and this is also f of E. Oh, sorry, I made a mistake, that it was L by f of O. So here we have L by f of O, length is 15 and f of O is 0.5. That's the correct expression. Now, when we solve this, we will get f of E is equal to 21.7 millimeter, and that will be nearer about 22 millimeter. So option A. In the next one, an observer looks at a distant tree of height 10 meter with a telescope of magnifying power 20 to the observer. Tree appears. So now for a telescope, what telescope does? It makes object m times nearer. Telescope is used to look at the distant objects, so it makes objects look near. So if it has a magnifying power of 20, so object will assume or appear to be 20 times nearer. That is option B. Now in the next one, to determine the refractive index of the glass slab using a traveling microscope, minimum number of readings are required. So uh, in this experiment, we required 3 readings, minimum number of readings, that are 3 readings. Now, first reading is for the base of the slab. Second reading is for the top of slab. And third reading is the top of slab plus sawdust. Why we need sawdust? Because when we take a reading, suppose this is the base of slab, we have taken the reading of base of slab. Uh, Sorry, not yes. When we take a reading for a base of slab with the slab there, so what will happen? We will not see actual base. We will see only the apparent depth. We not see the actual depth. We will see only apparent depth. That's why we need a third reading with a sawdust on it, so that we can find the actual height. So that's why we need 3 readings. So now the next one, a telescope has an objective lens of focal length 150 centimeter and eyepiece of focal length 5 centimeter. If a 50-meter tall tower at a distance of 1 kilometer is observed through the telescope in a normal setting, the angle formed by the image of the tower is theta, then theta is close to. So we have to calculate theta here. Now magnification will be equal to here FO by FE, and that will be equal to 150 by 5, that is equal to 30. Now alpha can be calculated with the help of this magnification, because magnification is basically equal to beta by alpha. Now how alpha can be calculated? Now suppose this is our eye and this is the this tall tower that is 50-meter high, and this distance between the tower and the eye is 1000 meter or 1 kilometer. So this angle will be going to be alpha here. So alpha will be approximately equal to, as angle is small, 50 by 1000. So this will be 1 by 20. Now using this relation, we can write that beta is equal to m times alpha, that will be 30 into 1 by 20. So basically 3 by 2, and it is in radian and we have to convert it into degree. So 3 by 2 will be equal to that is 1.5 divided by pi into 180, and this will give us around 84 degree. Now if you have to close to, so that will be option C. Now for the next one, we have a compound microscope of focal length of objective lens 1.2 centimeter, focal length 3 centimeter. When an object is kept at 1.5 2 centimeter from the objective, final image is formed at infinite or infinity. Magnifying power of the compound microscope is. So here we have f of O is 1.2 centimeter, f of E 3 centimeter, V of E, a final image of eyepiece at infinite, and U of O that will be negative 1.25 centimeter. So using the length formula, 1 by VO minus 1 by U of O is equal to 1 by F of O, and from this we will get 1 by V of O is equal to 1 by F of O plus 1 by U of O. Now this will be 1 by 1.2 plus 1 by negative 1.25, and solving this we will get V of O is equal to 30 centimeter. Now, in case of infinite image formation setting, the magnifying power of the compound microscope is minus of VO by UO into D by FE. So this will be minus 30 by U of O, that is negative 1.25, into D, that is 25, and F of E, that is 3. When we solve this, we will get 200. So option A is the right one here. In the next one, the focal length of the objective lens of eyepiece of a Galilean telescope are respectively 30 centimeter and 3 centimeter, for the telescope produces virtual erect and an object situated far away from the at least distance of distinct vision from the eyepiece. In this condition, magnifying power of the Galilean telescope will be. So for the Galilean telescope, we have magnifying power is equal to FO by F of E into 1 minus FE by D, and that will be equal to 30 by 3, 1 minus 3 by 25. Solving this, we will get 8.8 centi. Oh, sorry, 8.8. This will be 8.8, and that is positive. So option D. Now, the question has statement 1 and 2 of the 4 choices given. After the statement, choose one best described two statement. Very large size telescope are reflecting telescope instead of refracting telescope. So, yes, one is true here. It is easier to provide mechanical support to large size mirror than the large size lens. Yes, statement 2 is also here. And statement 2 correctly explains statement 1. So both are true, and 2 is a correct explanation of 1, that is option C. Now moving to the next one. Focal length of the objective and an eyepiece of a telescope are 50 centimeter, 5 centimeter respectively. If the telescope is focused for distinct vision, means final image at minus 25 centimeter on the scale distant 2 meter from the objective, the magnifying power will be. So here we can say F of O is 50 centimeter, F of E is 5 centimeter, and here U of O is 2 meter, and that will be negative. So using the lens formula, we can write that 1 by V node is equal to 1 by F node plus 1 by U node, that will be 1 by 50 and plus 1 by negative of 200. From this, we will get V node is equal to 200 by 3. Now, using the same lens formula for the eyepiece, we can write that 1 by U of E is equal to 1 by VE minus 1 by F of E. This will be equal to 1 by 25 minus, and this is negative already, so minus, and here we will get 1 by 5. So from this we will get minus 6 by 25. So U of E becomes 25 negative by 6. Now magnifying power will be magnifying due to objective into magnifying due to eyepiece. So M of O will be equal to V of O, that is 200 by 3, by U of O, that is 200. Now into V of E, that is 25, we are taking magnitude only, and divided by 25 by 6. So this 25 get cancelled, 200 gets cancelled, and we will get 6 by 3, that is basically 2. and it matches with the option D here. So option D will be the right one here. Moving to the next one. Telescope of aperture of diameter is focused on a window 80-meter distance fitted with a wire mesh spacing 2 into 10 to the power minus 3 meter. Lambda is given. Which of the following is true? Observing the mesh through the telescope. So now limit of resolution is equal to 1.22 lambda by D. So that will be equal to 1.22 into lambda, that is 5.5 into 10 raised to the power minus 7 divided by D, that is aperture diameter 3 into 10 raised to the power minus 2. So this will be equal to 2.23 into 10 raised to the power minus 5. Now this 2.23 into 10 raised to the power minus 5 is basically the angle, and it should be equal to arc by the radius. So arc here and radius is 80. So if we from this we will find that arc or the spacing that can be resolved is 1.78 into 10 raised to the power minus 3, and that is smaller than the wire mesh spacing, so it is not possible to resolve it. Now moving ahead, we wish to make a microscope with the help of two positive lenses, both of the with focal length of 20 millimeter each, and the object is positioned 25 millimeter from the objective lens. How far apart the lens should be so that the final image is formed at infinity? Now, suppose we need final image at infinity. So for the eyepiece, the image by the objective such that this image is at the focus of eyepiece, and now the focal length of both of these is 20 mm, so this distance becomes 10 mm. Now we have to just calculate this distance for the image distance for the eyepiece. Now object distance is 25 mm, 25. So we can write 1 by v minus 1 by u by 1 by is equal to 1 by f for the objective. So this will be equal to 1 by v equal to 1 by f plus 1 by u. Now 1 by f is equal to 1 by 20. Oh, sorry, this will be 20 here because focal length is 20, and plus 1 by negative 25. So this will give 100 LCM. This will be 5. This will be 4. This will give us 1 by 100. So V of objective is 100 mm. Now we have additional distance of 20 mm. So total distance will be 120 mm. That is option C. In the next one, we have an experiment is performed to find the refractive index of glass using traveling microscope. In this experiment, distances are measured by. So we measure vernier, option A, vernier scale provided on the microscope. With the help of vernier scale, we measure the distances. Now, image formed by the objective of compound microscope. So the objective of a compound microscope forms a real and inverted image. So that is it will be real and diminished because normally object is at very large distance, so its image will be small in size. Now coming to the last one, an astronomical telescope has a large aperture too. So to have better resolution, so for that we have high resolution. So option B is the right answer. So with this, this chapter is complete. Hopefully you like this video. If you have any doubts or suggestion, you can put them in comment section. I will like to resolve them. And if you find this video helpful, useful, then do press the like button, share it, and subscribe to our channel. Also, if you like to donate us something, you can scan these QR codes in front of your screen. With this, again, thanks for watching, and we will meet in next video.